Good morning, everybody. Myself, Vanika, selection grade lecturer in ENC department and in charge HOD, Government Women's Polytechnic, Kalburgi. Today, we'll discuss about the session 2 of course outcome 2 and unit 2, that is radar principles and applications. So today, we'll discuss about the radar range equation and we'll derive an expression for the radar range equation. So already we know what is meant by radar. So radar are nothing but the electromagnetic waves used to detect the target. Then what is meant by range? So here the range is nothing but the distance between the radar and target. The radar is nothing but gathering of information about distant objects or targets by sending electromagnetic waves at them and analyzing the echoes. The radar consists of transmitter and receiver, each connected to the directional antenna. The transmitter is capable of sending out a large UHF or microwave power through the antenna. The receiver collects as much energy as possible from the echoes reflected in its direction by the target and then processes and displays the information. So here in the figure, we can see the transmitter which transmits the radar signal and it is received by the distant target and the target reflects the radar signal and which is received by the radar. The radar range is observed by measuring the time it takes for the radar signal to travel to the target and return back to the radar. Radar range equation is useful to know the range of the target theoretically. So the distance between the radar and target is called the radar range. So here a master timer controls the pulse repetition frequency. So here you can see the pulses, a train of pulses. These pulses are transmitted by antenna at the target, which can reflect some of the energy back to the same antenna. So after the radar pulse has been transmitted, a sufficient rest time must be allowed for the echo to return. So as not to interfere with the next transmit pulse. This pulse repetition time determines the maximum distance to the target to be measured. So the duration between the two clock pulses should be properly chosen in such a way that the echo signal corresponding to the present clock pulse should be received before the next clock pulse. So here you can see in the figure the train of pulses. So here the distance between the two clock pulses should be such that the echo signal due to the first clock pulse should be received earlier than the second clock pulse. So next, let us go to the derivation of the radar range equation. So here, to determine the maximum range of the radar, it is necessary to determine the power of the received echoes and to compare it with the minimum power that the receiver can handle and display satisfactorily. So here, let Pt be the, here we can see the equation power density from isotropic antenna. So here power density is nothing but the power density at a distance r from the radar. So which is equal to Pt divided by 4 pi r square. So here PT is nothing but here the transmitted power, and 4 pi r square is nothing but the surface area of an imaginary sphere. Now the power that is transmitted from the transmitter reaches the target and it strikes the target. So the power density PD at the target from the antenna with a transmitter gain G is given by power density from directive antenna is equal to PTG divided by 4 pi r square. So what is meant by G here? G is nothing but is the maximum gain of the antenna, which is equal to maximum power density radiated by an antenna divided by power density radiated by an isotropic antenna. So here you can see what is meant by PT. PT is nothing but the transmitted power. G means G is nothing but the gain. So 4 pi r square is nothing but the surface area of the sphere. So here the power density of the echo signal at radar can be written as, so once the power reaches the target, it is reflected back and that is called as the echo signal. So here the echo signal is given by PD into sigma divided by 4 pi r square. So here the measure of the amount of incident power intercepted by the target and re-radiated back in the direction of the radar is denoted as the radar cross section sigma and is denoted by PE. That is, here power density of the echo signal is represented by PE. So PE is equal to, that is, PTG divided by 4 pi r square into sigma divided by 4 pi r square. So here where PT is nothing but the transmitted power, G is the gain, and so here is sigma is nothing but the cross-sectional area of the target and R is the range. So here, if the effective area of the receiving antenna is denoted by AE, the power PR received by the radar is PR is equal to P into AE. So already we know that the signals are received by the receiving antenna. So here, let the area of the receiving antenna be AE. Then we have PR is equal to P into AE. So let us substitute the things. PR is equal to, so the value of P is substituted here, that is PTG divided by 4 pi r square into sigma by 4 pi r square into AE, which is equal to PTG AE sigma divided by, so here you can see 4 pi into 4 pi is nothing but 4 pi the whole square. Then r square into r square is nothing but r to the power of 4. So the maximum radar range R max is the distance beyond which the target cannot be detected. So here we are deriving the equation for the R max, that is the maximum range that the target can detect, beyond which the target cannot be detected at all. So it occurs when the received echo signal power P just equals the minimum detectable signal S minimum. So here when the maximum radar range is reached, then the received signal is minimum. Received detectable signal is minimum. So let us call it as SE. Then what we have? So let us return R as R max to the LHS, and then we'll bring all other things to the RHS. So it will result in the equation R, that is maximum range R max, is equal to fourth root of Pt G sigma AE divided by 4 pi the whole square into S. So here we have Pt is nothing but the transmitted power, G is nothing but the gain, then sigma is nothing but the area of the target, and AE is nothing but the this area of the receiving antenna. Then S is nothing, S minimum is nothing but the minimum detectable signal. So we have R max is equal to fourth root of Pt G sigma AE divided by 4 pi the whole square into S minimum. So all of you understood? So here we can see that the effective area of the receiving antenna is denoted by PR is equal to P into AE. So let us substitute the things. PR is equal to, that is the received power is equal to PTG divided by 4 pi R square into sigma divided by 4 pi R square into AE, which is equal to PTG AE sigma divided by 4 pi the whole square into R to the power of 4. So this simplifying the things will get R max is equal to. So here when the radar range is maximum, then the received signal will be minimum. So we'll substitute it as S minimum. So we have, so keeping all the things, so here on the LHS we have R max, and on the RHS we have the other things. So by simplifying the things we'll get R max is equal to fourth root of PTG sigma AE divided by 4 pi the whole square into S minimum. So already we have derived it, that is R max is equal to fourth root of PTG sigma AE divided by 4 pi the whole square into S minimum. But we know that AE is equal to G lambda square divided by 4 pi, and the gain G is equal to AE 4 pi divided by lambda square. So substituting these in the above equation will get R max is equal to fourth root of Pt sigma A square divided by 4 pi lambda square S minimum. So this is the other form of the equation. So the equations represents the two forms of radar range equations. So by using this, we can find the maximum range of the target. So here you can see in the equation, so PT is the transmitted power, isn't it? So AE is nothing but the area of the receiving antenna. Sigma is the area of the target, isn't it? Okay, now we have derived an equation for the maximum range. Now let us go for the factors affecting the radar range. So what are the factors affecting for the radar range? So here we have the two equations. So seeing these two equations, we'll come to know that R max depends upon the PT, that is the transmitted power. It depends upon the gain, and also it depends upon the target. It also depends upon the receiver. So here we have, first let us go to the peak power. So here the decrease in the minimum receivable power will have the same effect as rising the transmitting power. So here the maximum range of the radar is proportional to the fourth root of the peak transmitted pulse power. So as the above equation says, isn't it? So here The maximum range is directly proportional to the fourth root of the peak transmitted pulse power. The peak power must be increased 16 times if a given maximum range is to be doubled, and then the maximum range capability of the radar increase with peak power. Next, we have the frequency. So, the higher the frequency of the radar wave, the greater is the attenuation. The lower the frequency of the radar wave are superior for longer detection ranges. So next we have the beam width. The beam width of the antenna is proportional to the ratio of the wavelength lambda to the diameter of the antenna. So any increase in the diameter to wavelength ratio will reduce the beam width. More the concentrated beam, the greater is the detection range of the radar. So the longer the pulse length, the greater is the range capability of the radar because of the greater amount of energy transmitted. Next, we have the receiver sensitivity. So here, ample time must be given between the pulses for an echo to return from any target located within the maximum workable range of the system. Otherwise, echoes returning from the more distant target are blocked by succeeding transmitted pulse. So here, since minimum receivable power P minimum is governed by the sensitivity of the receiver, minimum receivable power may be reduced by a gain increase of the receiver. So more sensitive receivers provide greater detection ranges but are more subject to jamming. Here antenna capture area. The above equation shows that the maximum range is proportional to the square root of the capture area of the antenna. So this is equivalent to doubling its real diameter if a parabolic reflector is used. So here targets that are large can be seen on the scope at greater ranges provided line of sight exists between the radar antenna and the target. So conducting materials, example, the steel, return relatively strong echoes while non-conducting materials such as wood return much weaker echoes. So here we have used the following references. So another one thing I want to say is noise also affects the maximum power range since it determines the minimum power that the receiver can handle. The other factors that should be taken into account are system losses, antenna perfection, receiver non-linearities, etc. The maximum practical range values is it varies from 10 to 100% of the theoretical value. So these are the references we have used for our material. So now let us go to the multiple choice questions here. So here the first question is, if the maximum range is doubled, then. So here we have three options. A option is the peak power is doubled by 2. B option is the peak power is increased by 16. C option is the peak power is doubled by 4. So here what is the correct option here? So if the maximum range is doubled, then the peak power has to be increased by 2. The peak power is increased by 16. the peak power is increased by 4. So you have to remember the equation for the maximum range, isn't it? The answer is the peak power is increased by 60. Okay, now let us go to the second question here. The range is option A, directly proportional to transmitted peak power, B, directly proportional to square of the transmitted peak power, C, inversely proportional to fourth power of the transmitted peak power. So remember the equation you have derived. So what is the correct option? Whether A, that is directly proportional to the peak power, B, directly proportional to the square of the transmitted peak power, C, inversely proportional to fourth power of the transmitted peak power. So what is the correct answer? So remember the formula. So here we have inversely proportional to fourth power of the transmitted peak power. So here you can see the equation, isn't it? Here it is inversely proportional to the fourth power of the transmitted peak power. So next we have question number 3. To get the range of the radar as maximum. So option A, peak power transmitted by the radar should be high. Option B, peak power transmitted by the radar should be low. Option C, peak power transmitted by the radar should be zero. So what is the correct answer here? To get the range of the radar as maximum. So peak power transmitted by radar should be high, it should be low, it should be zero. So think, what is the answer? The answer is A. Peak power transmitted by the radar should be high. Obviously, if the power transmitted by the radar is high, then we'll get the maximum range. Question number 4. We have to get the range of the radar as maximum, receiver bandwidth should be option number A, high, option number B, low, option number C is zero. So what about the receiver bandwidth? It should be high or low or zero. What is the correct answer? The receiver bandwidth should be high, isn't it? The receiver bandwidth should be high. So, okay, next question. Question number 5. If the peak transmitted power in a radar system is increased by a factor of 16, the maximum range will be increased by a factor of A, 2, B, 4, C, 8, D, 16. What is the right answer? The answer is A, 2. Next, we'll go to the next question. Question number 6. If the ratio of the antenna diameter to the wavelength in a radar system is high, this will result in, so here indicate the false statement here. So A, large maximum range, B, good target discrimination, C, difficult target acquisition, D, increased capture area. So which is the right option here? So large maximum range, good target discrimination. So the maximum range will be in A option, large maximum range. In the B option, good target discrimination. C means difficult target acquisition. D means increased capture area. So which is the right answer here? So A, increased capture area. Next, question number 8, we have flat-topped rectangular pulses must be transmitted in radar to indicate the false statement. A. Allow a good minimum range. B. Make the returned echoes easier to distinguish from noise. C. Prevent frequency changes in magnetron. D. Allow accurate range measurement. So here, what will be the right answer here? Hmm? So first option is A. Allow a good minimum range. B. Make the returned echoes easier to distinguish from noise. C. Prevent frequency changes in magnetron. D. Allow accurate range measurement. So the right answer will be make the returned echoes easier to distinguish from noise. Next we have the question number 9. If a return echo arrives after the allocated pulse interval, so what will happen? A. It will interfere with the operation of the transmitter. B. The receiver might be overloaded. C. It will not be received. D. The target will appear closer than it really is. So here what may be the right answer here? Hmm? So here, so when the first clock pulse is transmitted, then the echo signal should arrive from the target, then only the next clock pulse has to be transmitted. So if that operation does not take place, then what will happen here? So option A, it will interfere with the operation of the transmitter. Option B, the receiver might be overloaded. C, it will not be received. D, the target will appear closer than it really is. So the right answer is A, the target will appear closer than it really is. Okay, we have come to the end of our session. So I'd like to thank you from on behalf of all our team. Thank you. Thank you very much.